one, and then, sorry, so, we need to come up with some ordering, because we're going to put I, J, we talked about I equals two, J equals one, what this means, so, sorry, I don't know what to write it here. U1 is going to be referring to this variable, and then we can say U2, you could have flipped these, it wouldn't matter, you get like slightly different results, but the symmetry would balance it because of this thing right here. So this is just so that we can, nice and easy for us to do our computations right here. And then, so once we compute this, where are we right here? This one goes to 0, and then this would become that's one more.
Very good. Very good.
And then there's another one too as well. Let's see right here. Let's see the other ones. Okay.
So for sanity checks, so let's try to understand what is really going on here. So I'll try to explain the big picture eventually. So without asking the intuition of the sectional curvature, so let's just look at the expression of the sectional curvature together. So the denominator consists of so-called the first fundamental form or the Riemannian metric. So as long as you already know the inner product of each tangent spaces, then the denominator is already determined. So let's just ignore it for a moment. For numerator, the Riemannian curvature tensor indeed plays a role. So let's do not ask about the intuition, but let's try to appreciate the formula. So the Riemann curvature tensor should be consist of the so-called the Christopher symbol, okay? Christopher symbol and its derivative, okay? Whatever that is. So in order to determine the numerator of the Riemann curvature tensor, then all you need to know is just nothing but the Christopher symbol. And when you look at the expression of a Christopher symbol in the right-hand side over there, the Christopher symbol is purely determined from so-called either the first fundamental form or the Riemannian metric. So if you have a motivation to calculate the sectional curvature, then all you eventually need to know is the Riemannian metric, because once you know the Riemannian metric, say G each ij, then you will determine the Christopher symbol, okay? Then for each ijk with any indices, then as long as you know all of the gij, then you should be able to determine each Christopher symbol. Then you should be able to determine the Riemann curvature tensor for each indices. Then you should be able to determine the numerator of the sectional curvature. And now you see the reality. So the reality should be the following. So all you have is just nothing but certain massive metrics over there, say Gij, right? In the case of just the two-dimensional like torus, because this is now two-dimensional, so the matrix just is the rank 2. Okay, so and that expression should be explicit. Got it? So once you have the Riemannian metric, then you should be able to determine the explicit Christopher symbol. Then you should be able to determine the explicit Riemann curvature tensor. And those calculations nothing but either taking derivative or taking certain linear combination. So it's purely calculus. Got it? It's pure calculus. And then you should be able to determine the sectional curvature. So 90% of the graduate students who take the Riemannian geometry in the graduate level never actually did this calculation before. And this is actually a major obstruction why they cannot really understand what was going on. So without asking the meaning, the very first thing in order to learn the Riemannian geometry is to just proceed this calculation all by yourself. Especially it's good to check why either the n-sphere, n-dimensional sphere, or the torus, or the Euclidean space, or the bore has a constant sectional curvature. That's actually quite subtle. And not just knowing as a fact, is extremely important to do the calculation to learn Riemannian geometry. So that's why for Semi, because he never actually took even undergraduate differential geometry, but just asked him to just proceed the calculation of the Gaussian curvature and the sectional curvature without even knowing the meaning. That's actually the most hardest part because we do not know the intuition yet, but still we can proceed the calculation step by step. Okay. So once you finish this calculation, it's like putting the hello word with the Python without knowing the assembly language. Okay, so once you know how to do it, then you will later understand what was really going on here. So I think that's enough for today. So I'll try to explain what you're actually doing. Okay.
Okay.
So yeah, my turn. So I will try to explain what was really going on here. Okay, and unless I make the record so that you can later take a look. So let me try to explain intuitively what was really going on. And even though the calculations here are purely from the calculus indeed, not even the taking integration, all those are just taking a bunch of the derivatives and just putting some linear combination. However, this is indeed coming from the Riemann's core of his work. So let me try to give you the intuition first, so-called the Gaussian curvature. And I'd like to compare with his calculation today together. So let me start from the example. So either the sphere, okay, either the sphere or the Euclidean space, say two-dimensional Euclidean space. Okay, it expands to the infinity. And you can also look at either the operable plane. And we are now running the seminar with the title Information Geometry. So this one is the same as the collection of the one-dimensional distribution as the first presentation. Okay, so it has a significant meaning eventually. And torus. So our purpose is to distinguish one from the others. So how? So I'd like to say all those spaces must be different. And I'd like to say in terms of the so-called Gaussian curvature. So the intuition is the following. So you can choose arbitrary point. Here. So let me just choose any point. Okay, choose any point. So let me first explain without using any formula. Okay, so then what you need to do is consider any possible so-called C2 curve. So that I'd like to consider any curve passing through the fixed. Got it? So you can really imagine what it should be. So that at least in the case of the two-dimensional sphere, there's no straight line. Agree? Whereas over here, you can definitely take the straight line. Of course, you can also take a curve, but at least the choice of the straight line would be available, not like the sphere case. You agree? And also here, there will be some weird curve here, and also the curve might behave something like this. And let me also draw the cylinder here. So I'm just talking about the work here, so that if I choose the point here, then either one curve would be something like this, the other one might be like this. And we'd like to talk about the curvature. So what is the curvature intuitively? Curvature means the magnitude of the second order derivative. You agree? Curvature should mean nothing but the acceleration. Acceleration physically means the second order derivative. You agree? So that from the calculus point of view, either you have this one. We prefer to call such a curve so-called convex. Got it? Or this one. We'd like to say this is flat. No curvature. We'd like to say this is concave. And we can distinguish all of them by just looking at the sign of the second order derivative of the chosen point. You agree? And in the case of the two-dimensional surfaces, so there are plenty of choices of the curve. So that I'd like to look at all possible second order derivatives. Is that clear? So for example, here, what is the curvature here? Curvature should be 0. Do you agree? Curvature should be 0. Whereas if you look at any possible curves here, there's no straight line. So that the second order derivative must be at least non-zero. And let me just try to explain naively so that all those like the magnitude must have the same sign. Is it clear? And I'd like to just choose the maximum second order derivative. And also the minimum second order derivative among all possible curves. Is it clear?
And in fact, whatever curve you actually choose, those two actually are the same in the case of the two-dimensional sphere. So that if you multiply by them, so this is the definition of the Gaussian curvature. Okay. So it's very hard to grasp the meaning from the formula if you look at the undergraduate differential geometry textbook. But indeed, the quantity of the Gaussian curvature at each point just means we will just multiply the maximum second order derivative by the minimum second order derivative. Got it? So that in this case, so it seems all magnitude must have the same sign. So the Gaussian curvature is in fact positive constant everywhere because this is totally symmetric. I just try to explain indeed naively, but you should be able to verify from the formula of the Gaussian curvature. And for your own self-study, you can really try to connect why this type of intuition really works for the messy expression of the Gaussian curvature. For example, this case, there exists the choices of the straight lines so that you can make the curvature, at least one of them, to be zero. So the Gaussian curvature of each point on the plane should be zero. Is it clear? And over here, of course, there is also possible choice of the straight line. So that whatever curvature of such a curve, I mean the sign, I don't care because I already know one of the straight line must have the zero curvature. And once I multiply by them, so the Gaussian curvature of the cylinder should be zero. Is it clear? So that in some sense, we'd like to just say there is a way to identify those two, because if you have like a paper, then you know how to like make it to be like a smoothly, right? So that it seems like the cylinder and the plane are somehow so-called isometric, meaning that geometrically, in fact, they are the same. And we can capture the feature by just looking at the same Gaussian curvatures, because all those have the zero Gaussian curvatures everywhere. Is it clear? And this is the interesting model because one of the curve has a positive curvature, the other has a negative curvature. And this is true for all points. So this has a very interestingly, this has a negative constant Gaussian curvature everywhere. Meaning that you can always choose the point it behaves as a static point for the upper plane. Got it? So it might not be easy to believe, but you should be able to check if you are really serious. And in the case of the torus, so there is a first fundamental form or the Riemannian metric that makes Gaussian curvature equal to zero everywhere, surprisingly. Okay, so that at least by using the notion of the Gaussian curvature, you should be able to distinguish at least certain spaces for the surfaces.
So how much of this is dependent on your choice of metric?
Very good question. Of course, the most important theorem of the undergraduate differential geometry called the Gauss. This is indeed the name of the theorem. Gauss is remarkable theorem. Okay. As Sammy presented someday before. So according to this theorem, so this theorem says that Gaussian curvature is completely determined. What do you expect? By Riemannian metric. Okay, so the Riemannian metric, this notion just means that once you have just a surface, so Riemannian metric is the family of the inner product for each point. So for each point on the surface, you should be able to create the tangent space by taking the certain linearization. Then we will just look at each inner products and we collect all of them and we will call it by the Riemannian metric. And the Gauss remarkable theorem says that as long as you already know the Riemannian metric, this totally determines the Gaussian curvature. This is somehow astonishing in the following sense. So before I try to erase the board, so I want you to appreciate the intuition. So that from the perspective from the calculus, the Gaussian curvature indeed try to capture the shape of the given surface. Got it? So in some sense, Gaussian curvature is used to say, in some sense, we can see they might not be different. For example, because once you calculate the Gaussian curvatures, they are the same. I mean, there is a zero curvature. But if you try to compare the R2 with S2, for example, they definitely has a different Gaussian curvature. So that we can say they are clearly different in some sense. But in some cases, they might be the same. But it depends on the choice of the Riemannian metric. So that it gives some way to classify the chosen, like the given spaces. So Riemannian geometry and all kinds of the geometry is to classify the given spaces. And the Riemannian geometry is to classify the spaces from the shape, and the shape would be completely different from the Riemannian metric. And at least the Riemannian metric will determine the Gaussian curvature completely. So the Gaussian curvature would be one of the possible invariant to classify the spaces from one to the others. Is it clear? But you first need to appreciate this type of the intuition without looking at the formula. And now let me give you the expression of the Gaussian curvature to appreciate why this theorem is significant. So let me erase this board. Let me know if you have any questions. Okay, but you already saw from the Sammy's presentation already. So once we know the Riemannian metric, so it was possible to determine the sectional curvature. So without looking at the expression of the sectional curvature, what should be the sectional curvature? So Gaussian curvature only works for two-dimensional case. Okay, so if you try to generalize this to the n-dimensional, this we call it by the sectional curvature. In the case of the two-dimensional case, sectional curvature coincides with the Gaussian curvature. Okay, so that we just want to generalize this intuition to the n-dimensional case. That's we call it by the sectional curvature. Got it? It's I think about the same with the two-dimensional cases. So let me try to explain why this theorem is indeed remarkable. Why? The reason is the following. Let me try to explain with two pictures. So suppose you never saw the picture of the moon. Okay, so we never saw it, and we want to conjecture that the sphere, I mean the planet Earth, should like the shape, something like that. But let us suppose we never saw the picture. So then how can you deduce such a shape? So one possible way is that if you know the Gaussian curvature, got it? If you already know the Gaussian curvature, then as long as it has a positive like a curvature, that means that each point, it looks something like this, right? So that if you are able to calculate the Gaussian curvature everywhere, then you can deduce the shape. As long as you know each point Gaussian curvature is positive. So that it should shape something like this. Is this possible to imagine? But according to the Gauss's Riemann curvature theorem, all we need to know is nothing but what? All we need to know is the data of the Riemannian metric. What is the Riemannian metric? This is the information of the tangent space. So what the heck was going on here? So you are just standing on the Earth, and you just look at the data of the tangent space. You never go outside from the Earth. But as long as you know the data of the tangent space, you should be able to deduce the shape of the Earth without looking at the picture of the Earth. That's what this theorem means, right? We never look at the normal direction. We have no data to the normal direction ever. But according to the data of the Riemannian metric, according to the theorem, you should be able to deduce the Gaussian curvature. And once you know the Gaussian curvature everywhere, you should be able to deduce such a shape. So without going outside from the Earth, you should be able to understand the shape of the Earth. Still, there are some people who believe the Earth shape would be flat, but yeah, it's really like, let me do not explanation. Okay, so this is one thing you can see. And now let me give you the expression of the Gaussian curvature so that now you can appreciate why this is really, really remarkable. So this is also presented by from Sammy before. So let me just draw just a general surface. Okay, general surface. So let me choose the point. Then according to his presentation, at least we should be able to find the small board here. Okay, in R2. So that we'd like to identify this board as just the neighborhood of this point. You agree? So that I should be able to, for example, identify the small like the u-axis as just a curve here. So I intentionally draw the picture so that you can appreciate the intuition. So for this guy, there should be corresponding at least some linearly independent direction. I'm sorry, this is V constant and here is U constant. Agree? Is it clear? So that we identify those two balls already for each point on the given general surface, of course, including either the S2 or torus, but I just try to address just the intuition. Just this is just general surface. Then what can you do? So I'd like to, and this map is usually called by just R. So this is the one-to-one correspondence from here to here. So that takes U and V. Got it? U and V. And the output belongs to R3. So that you should be able to do either the taking derivative or taking integration, because this is just a purely from the multivariable calculus. So then I should be able to take the partial derivative with respect to U, and also the with respect to V. You agree? Because it takes us two inputs, and the outputs are just three components. So by taking each partial derivative, you know how to take it. So let me just even give you the formula. So for example, if you plug in any input inside of this ball, then because it belongs to R3, so that there is a X component, Y component, and Z component. You agree? For each UV. And you know how to take the partial derivative. So that means you just need to take the partial derivative on each component. Same for V. Got it? But let's just try to imagine how would be the corresponding picture. So what's the meaning of taking the partial derivative with respect to U? That should mean this one. You agree? This is just the infinitesimal direction along the U-axis. What about this guy? This guy corresponds to this one. You agree? Even the mathematical operations are pretty simple, so that there are two inputs with the three components as an output, and you know how to take the partial derivatives. But when you imagine the picture, what was going on in the surface, then you just take the infinitesimal directions with respect to U-axis and V-axis. And you should be able to do it for any points, because each point you should be able to just identify a certain ball in the UV plane. Is it clear? So that we have at least two linearly independent vectors. You agree? And we already make this surface inside of R3. Of course, this is eventually not necessary assumption, but this gives us the reasonable the intuition. So what do we expect? So one direction might be something like this. The other one might be something like this. So that at least those two should be linearly independent. You agree? Because they are coming from the different directions. So that we can generate two-dimensional plane, but now we make the situation sit inside of R3. And we know we can create the direction which is perpendicular to any of those two directions. How? We know how to take the cross product. You agree? I try to address our issue from the just a purely calculus point of view, so that the normal direction would be nothing but taking the derivative, cross product, and just take the normalization. You agree? So that for each point, you should be able to find this map, and you should be able to find the uninormal vector field. You agree? This can be done explicit as long as you have this out. Is it clear? So I'd like to make the intuition really clearly. So given surface, including the torus, so Sammy already gave the explicit such the description of such R. Then you should be able to take the derivatives, right? With respect to U and V, it's definitely possible. Then you should be able to take the cross product. This is one of the vector inside of R3, so that it has certain magnitude, so that you can divide by it, so that you can make always the magnitude of this guy equal to 1. For each point, that's always possible. Do you agree? Then what I will do is I will simply just take so-called Jacobian. So this just means I will just simply take this guy. Okay, and this becomes the 2x2 matrix. And let me now give you the rigorous definition of the Gaussian curvature, not without the intuition. So Gaussian curvature this is in fact the real definition, is determinant of n. This is the definition. Okay, and just to go back and try to think why this coincides with the explanation I already provide. Okay, so those are exactly the same. So why this is something really surprising? So this is the linear operator eventually, so that you should be able to take the determinant. This is nothing.
You can determine it as a product of eigenvalues.
Yep, that's one of the reasons coming from the spectral theorem, as you mentioned someday before, right? But what is surprising? So in order to define such a quantity, then you should look at the unit normal direction. So in order to consider it, you should know what? You should know the data outside from the tangent space. You agree? So what I said is that, so we first create two linearly dependent directions first, and then we are looking at the direction outside from the tangent space. Is it clear? And we denote it by the capital N. And the dividing by the magnitude is just nothing but the scaling. And then we take the further derivative, and then we just look at the determinant. This is the definition of the Gaussian curvature. When you look at the theorem, what do we need to know? All we need to know is the data of the tangent space. So this theorem says that even though we calculate the Gaussian curvature, and you can now later check the way you calculate the Gaussian curvature before, so you already used the cross product. However, according to the theorem, we actually do not need to look at the data outside from the tangent direction, tangent space, like the deformation. So in that sense, this is surprising. So when you need to know the shape of the Earth, so one possible way is, as long as you know the direction outside, normal to the Earth, that's definitely possible for you to deduce the shape. But according to this theorem, all you need to know is the data of the tangent spaces. So that's why the spirit of the sectional curvature, so all you actually use is not the normal direction. You just use the Riemannian metric, right? That means that the data sit inside of the tangent space. But still, you should be able to deduce the sectional curvature, which is the same as the Gaussian curvature. So this has a powerful the implications. For example, so as long as you know just the information of the inner product, I mean the tangent spaces, then you can deduce all possible the geometric structure of the given the spaces, including the statistical models or whatsoever, so that you should be able to use this data. And the purely data is, I think I call it the certain matrices. It's indeed just using the calculus or the linear. So yeah, let me know so far if you have any comments or questions.
It's just the question. So how do you usually find the data on the tangent space?
So it's a while, but it's good question, to be honest, because another name of the Riemannian metric is so-called the first fundamental form, meaning that it is the most important the invariant of the differential geometry. So it's definitely important to ask about the meaning of either the Riemannian metric or the first fundamental form. So now let's look at, so in order to address your question, so let me also look at the surface inside of R3. Okay, inside of R3. So how do you view R3? R3 is somehow the perfectly flat three-dimensional space. You agree? But so that we already assigned the geometric meaning in this space already. But according to linear algebra, so what we learned is that as long as we have a vector space, then we put the inner product to what? To consider the notion of the magnitude. You agree? And to consider the notion of the angle. So in order to put the geometric quantities, you should first assign certain inner product on the given vector space. Agree? R3 is the vector space. And we already view R3 as a perfectly flat three-dimensional space, so that you already assign certain inner product. Otherwise, it doesn't make sense to talk about this space is flat, because you already put the certain geometric quantities in your intuition, right? You already view, for example, 1, 0, 0 should look something like this. 0, 1, 0 should be something like this, and 0, 0, 1. So that all they are perpendicular to each other, and each of them has a magnitude equal to 1. Why this is possible? Because you already put certain inner product. What is it? That's the dot product. So without using the dot product, you should not able to say this picture definitely makes sense. For example, if you change the inner product, you can make the magnitude of each direction to be equal to say 5. And you can even make those two directions are not perpendicular. There's no guarantee. So this picture only makes sense when you use the dot product. Is it clear? So this is where the very first, like the starting point of like the looking at this space geometrically. So you already put the dot product over here. So you already view R3 ambient space by using the dot product. So you also view this surface by looking at just with the viewpoint from the dot product. Is it clear? So that's why. Let me just draw the same picture for each point. Then I will identify this neighborhood with the more in UV plane. Like this. So that from this map, R, that takes UMB. One direction is coming from DRDU. The other direction should come from DRDB. Agree? And intuitively, we already believe those two should be linearly independent, but we'd like to put the geometric quantities from those two, so that I'd like to just look at one is the dot product between same vectors, this guy, and another one is the effect of the crossing terms. Here is U, here's a B. The other one is this guy. The last one should be this one. Got it? So that we just collect all possible like the choices from using the dot product. So what's the name of this matrix? This is the Riemannian matrix. Okay. And in some sense, we already view the R3 by using the dot product, so that we indeed visualize the relation of those two vectors by using the dot product in R3. That totally makes sense. And this is also called by the first fundamental form. And according to the Gauss's remarkable theorem, as long as you know this 2x2 matrix, then you should be able to determine the Gaussian curvature completely. And you already proceeded the algorithm before in the case of the torus. And this can be even generalized to the n dimension by just considering the sectional curvature. Okay. And later on, as Sammy already used like notation the G sub ij. So this is usually denoted by G11, G12, G21, G22. By just replacing R sub U by 1, R sub V by 2. So here R sub U and R sub V just means the taking the partial derivative with respect to U and V. Okay. So this is just a preliminary for the information geometry. So at least what you are seeing is the way to calculate the sectional curvature. And in the context of the statistical models or the mathematical statistics, so most of the statistical model you are considering like the exponential family, mixture family, has the property that has a sectional curvature equal to 0. And by using that, you should be able to make certain algorithm really nicely. And for example, like the base, like the low placeable. So once you see this like the calculation, how to calculate the sectional curvature equal to 0 in certain cases, then we will just see how this works in the certain like the statistical context. That's the rest of the quarter I'd like to cover. Okay. And if you want to learn this subject, so not about asking the meaning. So I highly recommend you again to just proceed the calculation of the Gaussian curvature and the sectional curvature. And later on, you can just figure out what's the intuition and the meaning of it. And then there's a huge like the area and the field you should be able to work on. So yeah, that's the way we cover. So let me just try today finish the explanation why I just try to explain this material in this manner. So undergraduate differential geometry takes at least 10 weeks to learn it. Riemannian geometry takes at least 1 semester or even year to learn it. So if you just try just each line by line rigorously, you should not be able to learn it. So that's why I first just let students to just do the calculation of the sectional curvature in the beginning, without even knowing the meaning. I know this is a really sort of a torture, but still is necessary to understand what would be later on going on. Okay. So once you understand this calculation and that's just the behind meaning of it, then there are tons of like applications in the either statistics or machine learning. But So some of it I will try to cover the rest of the quarter. So yeah, let me know if you have any questions.
Sorry, I'm a little confused. Over there is the derivative and the 2x2 matrix.
Yeah.
Are they related to that?
So those two are different matrices. So the Riemannian matrix can be written as a certain symmetric matrix like this. And the Gaussian curvature is defined in terms of the derivative or the Jacobian of the normal direction, normal vector field. So those two are clearly different 2x2 matrices, okay? But the remarkable theorem of the Gauss says that, so this matrix, I mean, this value, so I'm not talking about the 2x2 matrix here, I'm talking about the determinant. Determinant of this 2x2 matrix is completely determined from this matrix. That's the remarkable theorem. And this is astonishing in a sense that in order to know this data, we should know the data of the normal direction, right? But the normal direction is the data outside of the tangent space. Whereas this data actually sits inside of the tangent space. So this data is sufficient to deduce this quantity, so that we should be able to deduce the shape of the surface. So the Riemannian geometry is to classify the spaces. So we rigorously call it by the Riemannian manifold. So we classify the Riemannian manifold in terms of the sectional curvature. That's what is the Riemannian geometry for. And the statistical context does certain statistical models satisfying the sectional curvature equal to 0. And based on it, so there's certain applications. So I just try to explain really like the intuition and the big picture. But yeah, so because of time limitation, I think this is the best
I
argument.
know you were trying to focus on the intuition rather than the details.
Yeah,
but,
yeah.
The normal vector, for example, there, what that you got by taking the cross product.
Yeah.
Must be naively, if I naively see it, that should be 3D.
Yeah, it only works for the 3D because we are using the cross product.
Mhm.
But the notion of the sectional curvature works for any dimension, so that one should see why the cross product can be eventually ignored, right?
But then if you take one more derivative, then
This makes sense.
shouldn't it be three-dimensional vector?
So this just means the following. So eventually, this is just a vector inside of R3, so that it consists of x, y, and z. X, y, and z. So I should be able to also take the derivative. So, but it has a rank equal to 2. I know I just explained really lightly, yeah. But it can be reduced as a 2x2 matrix.
Some details.
Yeah, yeah. I just try to explain just really like intuitive.
Similar direction. When you... No, never mind.
Yeah, the detail can be very long. That's true. So as you saw, the original expression of the semis calculation. Yeah, let me know if you have any other comments or questions. So from next time, so I'll try to now start to cover the core of the information geometry, assuming that you already saw the calculation of Gaussian curvature and the sectional curvature. But I know it really takes time. So if you want to learn this, like the type of the field, this is the intermediate field between the pure geometry and also the applied work. And this part is somehow most difficult part. It takes time. Usually it takes more than a year for the talented students. So I don't assume you really understand what was going on. So I highly recommend you to do the calculation of the Gaussian curvature or the sectional curvature in the case of the torus, and you should be able to drive the curvature of the torus is equal to 0. This is really important, okay? Without asking the intuition. Once you reach the calculation equal to 0 for the curvature, then you should try to link why the intuition really works for this calculation. But the reality is just a dirty calculus stuff. Yeah, that's the reality. So from next time, yeah, so I'll try to cover the details of the information geometry with this assumption. So is it okay? So, and if any of you want to learn this subject, so I highly invite you to do the calculation, and you can also proceed as Sammy did, okay? So you do not need to complete the calculation. It's just fine. So I just want you to just do the calculation all by yourself, okay? So that's always the reality of doing the research in the differential geometry direction. So you just need to know how to calculate the sectional curvature. Yeah, that's today I just want to say. So if you have no questions, so we can finish the queue.
Just one more quick question.
Sure.
So can you explain again why the Gaussian curvature for the upper half plane is negative?
So that's really important, okay? So you should check, okay? So that's really important fact that on the upper plane, the Gaussian curvature has a negative constant.
That with respect to the Poincaré metric.
Poincaré metric, yeah, with respect to the Poincaré metric. I know I really didn't explain anything, but when you just search, so there are tons of references you can look at, but not just trying to figure out like the look by just reading the materials. So I highly recommend you to do the calculation all by yourself. It's not difficult, okay? It's difficult to capture the meaning or the intuition, but doing the calculation is purely just a calculus. Okay, so once you do it, just bring during the seminar, then yeah, I will try to explain what's going on. Yeah. And now is your time. So not rather than just calculating the sectional curvature. So if you remember, one of the reference I shared in the very like the beginning is the introduction to information structure, right? What was the author? So author, yeah. So now it's possible for you to read that material. Okay, so
There are the selection of pages you want me to look at, or just keep.
you should look at everything. Yeah. So because we just want to like rephrase certain like the section for your senior thesis, but unless you'd like to get your own big picture, right? So that just look at really just briefly, but try to look at everything and make sure you should look at this.